Hello, my name is Dale Hume. I'm with Mathis Instruments Technical Services. The purpose of this video is to give you a brief glimpse at the Mathis Thermal Conductivity Instrument, the TC-30. I will introduce the TC-30 system components and walk through a calibration. Then using that calibration, we'll test a sample for thermal conductivity. Although the Mathis TC-30 does measure thermal effusivity as well, which is the square root of thermal conductivity, density, and heat capacity, we'll be focusing on thermal conductivity measurements in this video. That said, please keep in mind the calibration and testing routines for both conductivity and effusivity are very similar. So let's begin. Starting with the standards for the testing of solids, liquids, pastes, and powders, Mathis offers two calibration packages. First, the liquid calibration package for the testing of liquids, which consists of 6 standards that cover the bulk range of liquid samples. The next calibration package is for solids, pastes, and powders. This basic calibration package consists of 8 standards that cover a range of 0.04 to 1.1 watt per meter Kelvin. Mathis also offers an extended K range for samples above 1.1 watt per meter Kelvin. There are 3 sensor options for the Mathis TC-30. The external sensor shown here is the most widely used due to its sample size flexibility. With a minimum sample size of 1/4 by 2 inch and no maximum sample size restraints, it is easy to see why this is the most widely used sensor. The second sensor option is the stainless steel sensor. This sensor can be used to test powders or liquids. It can be used on the bench, or it can be used to test in situ, such as a pipe. The third TC-30 sensor option is the chamber sensor. This chamber is held at a constant 30 degrees Celsius. It is specifically designed for use in uncontrolled environments, such as the production floor. The last component of the TC-30 is the controller. This houses the data acquisition module and runs off of a Windows-based platform. This also runs the TC-30 software. As the TC-30 is a transient method, we have to ensure the heat generated by the sensor stays within the sample boundaries. In this case, our sample is 5 layers of paper. Therefore, we will use a technique called the Blotter Technique to discover the appropriate test time. The most important tool of the Blotter Technique is the blotter weight. This has an insulative side and a conductive side. The first step of the Blotter Technique is to place the sample in question on top of the sensor. Then, placing one side of the blotter weight on top, in this case, the insulative side. We will then choose a test time we know penetrates through the thickness and into the backing material. Then, by repeating this and flipping the blotter weight over on the conductive side, we will again look at the same test time, which will penetrate through the 5 layers of paper and into the backing material, ensuring that the consistent part of both tests is the 5 layers of paper. Let's take a look at the data. This graph represents the temperature rise versus the square root of time on the raw data that we just performed. I've saved those 2 data files and overlaid them on top of each other. As you can see, there's a very consistent portion of this line. This is where the heat is penetrated through the 5 layers of paper and deviated into the conductive or the insulative backing material. In this case, this gives us the total allowable test time for our 5 layers of paper, approximately 1 second. Now that we've determined 1 second to be the appropriate test time for our 5 layers of paper, let's calibrate the TC-30. The first step in calibration is choosing 3 appropriate standards from our basic calibration kit. In this case, I've chosen Elastofoam, HDPE, and Pyrex. Then, by placing each standard on top of the sensor and testing for a period of 1 second, which we determine with the Blotter Technique, we will have an instrument response against this thermal conductivity standard. Repeat this for each standard to get an instrument response for different conductivities.
This calibration table represents the collected instrument responses against each standard. There eventually will be 6 tests, as each standard is tested in duplicate to ensure reproducibility. We have one last test of HDPE to complete this calibration table. Let's go ahead and test that standard now. After initiating our 1-second test time, there is a real-time display of temperature rise versus time. Now that we've completed the calibration table, let's take a look at the calibration graph. This plots the instrument response, or the slopes of each test on each standard against each standard's thermal conductivity value. Let's take a look at the slope for HDPE. As you can see, there's a 0.5 second start time. This ensures we're beyond any effects of contact resistance between the sensor and the sample, ensuring we're in the linear portion of the temperature rise. Again, the slope comes from the start point to the end point of this line. Now that we've completed our calibration, I've went ahead and placed the 5 layers of paper on the sensor and performed 3 tests using the auto-test function. Upon completion, it displays the average data along with percent relative standard deviation. Our result is 0.11 watt per meter Kelvin with a percent relative standard deviation of 0.14. As another example of sample testing, I've placed a sample of polycarbonate on the sensor. Using the same 1-second calibration we previously created, I will perform 3 tests using the auto-test function.